Okay, welcome everyone. It's my pleasure to introduce Anna, who's going to be talking about the classification of rigid Frobenius algebras in the DW categories. Go for it, Anna.
Joachim Fahr, Nosva Infar, EPUB. So thank you to the organizers for inviting me again in the seminar. I'm really excited. I'm super happy to be back to the United States, if only for tonight and online. So yeah, today I would like to tell you a little bit about some recent work that we released. So together with Robert Lovewitz from Nottingham and Sam Hanna, who happens to be my PhD student. We released a preprint back in March last year, and in a record time, we got it published. I mean, I still cannot believe it. At Sigma, you can find this is the QR code to the link if you're curious. Let me mention that Sam is in the job market. So if you're impressed by this work, please, 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 this is your person to hire. This guy, it's amazing. I cannot recommend him enough. And so let's start. As the title suggests, well, I mean, many of you know that I have a long-standing love for algebra objects in tensor categories. I mean, the reason behind this, it's, well, probably because of my career. So like it's because they are very strongly related to several topics in mathematical physics. So probably the first time I heard about those, it was back in the day when I was studying full rational conformal field theory. So one kind of conformal field theory satisfying very nice properties that was there's these wonderful papers by Fuchs, Funk, and Schweigert and collaborators. I think it's 5-6 papers going into full glory of these kind of CFTs. And in this particular case, I mean, they classify this by simply two ingredients. So one is like a rational VOA, a rational vertex operator algebra describing the symmetries of the CFT, and an algebra object inside these category representations, the category representations of these VOA. So that was the first time I saw them, but then they appeared in many other places. So another one was related to extensions of vertex operator algebras. So that we know that they are in a one-to-one correspondence with algebra objects in the category representations of these VOAs. This was worked out by Huang, Lepowski, and Zhang, and extended to the supersymmetric context by Thomas, Shashank. Hey, Shashank, say hello. And and Robert. So more places, let me just mention because, well, they are my PhD brothers. Oh, they also appear in our spin topological field theories, I mean, by Sebastian and Lori, and of course, Ingo. And non-exhaustive list, I mean, there's plenty other places in classifications of TFTs and blah, blah, blah. But then if you just care about them on the, let's say, purely mathematical side, well, I mean, these guys, algebra objects, they are also classified module categories over these tensor categories. So together, you know, these seem like a very interesting topic. So why not? Let's have a look at these guys. The problem is that they are slightly difficult to find and classify, so which makes it more of an interesting problem. So of course, when we have classifications of algebras in certain different kinds of tensor categories, I will focus in a little bit on fusion categories. So a fast result by Ostrich and, I mean, years later, given concrete conditions by Sonia Natale, it's a case of vector omega. So this is the category of vector spaces, K vector spaces. They are G-graded. And I mean, the structure of the category is kind of controlled by a certain 3 ecocycle, taking values from this G. And this result classifies algebra objects, some algebra objects. In this category, they are exhausted by twisted group algebras. So a certain kind of group algebras where the multiplication is kind of tweaked by these extra some cohomological data. Actually, not too long ago. So it's going to be 4 years ago. Oh, wow. Time flew. I mean, together with a beautiful collaboration of the belonging to the woman in non-commutative algebra and representation theory. So with G.V., Moniki, Julia, Angela, and Chelsea, we also did a similar job. We performed a similar classification as Ostrich and Natalia, but instead of in vec G omega, in another kind of category, really not the same, which is the group theoretical fusion categories. And in this case, we had kind of like a similar algebra to before. In this case, it's something that we baptized twisted Hecke algebras. One can, actually, you can, how to say, I mean, if you simplify enough that you're setting, you actually recover the twisted group algebras. So, all right, vec G omega, that was a lot of fun in these two cases. So why not? Let's try something a little bit more exotic. So we focus, Robert, Sam, and I, in the case of the so-called Dijkgraaf-Witten categories. So this triumphal center of vec G omega. And actually, it wasn't particularly our first motivation, but actually, one of the referees, I mean, remind me that actually these guys were related to orbifolds of the so-called holomorphic VOAs whose representation category is actually vec. So if you have one holomorphic VOA, I mean, you have the representation category is vec. But then if you take G to be a particular group, I mean, related to the automorphisms of the VOA, and you perform a certain procedure, which is called orbifolding, then these category representations is actually this Dijkgraaf-Witten category. This was first conjectured by Dijkgraaf, Pasquier, and Rocher, and then proven progressively, like under certain conditions, by Sven, Jethro, Sven, Niels, Dongeng, and Rang, in full generality. And I mean, but actually there's some technical conditions here to be considered, to be taken into account. I mean, it's in full generality, not yet, but I mean, in the case of the geosolvable, I mean, this has been proven by Miyamoto, Carnahan, and Robert. All right, so what we want to remember, this message of the day, we want to classify algebra objects in these categories. And the how is actually, we want to use something called Frobenius monoidal functors. So like more of a functorial tool than just more like an algebraic, representation, theoretic attacking. So I will go and explain. I mean, I usually work more with categories than with VOAs. So I will just go in like a little bit of detail on the categorical side, so everybody comes with me hand by hand. So let's start. Oh, by the way, let me just, before I forget, let me just say that we knew that there were some algebras in here, and this was worked out by Davidoff and Simmons, but the thing is that we wanted to, I mean, describe these and classify these in full generality, because they only did perform this classification for arbitrary for characteristic 0. We do this for arbitrary characteristic and in a much more explicit way, or at least for my taste. So let's start. Let me just refresh a number of concepts. So, I mean, by a monoidal category, what I mean is a tuple. So my category, a certain bifunctor going from 2 copies of the category to C, to the category back, a distinguished object, which we will call a unit, alpha, which is a family of natural transformations that relates the product of 3 objects. So if you take 2 and multiply them and then multiply them with a third, you should be relating this to the second and third multiplied together first and then with the first one. This family of natural transformations are called the associator. And then some morphism, and again, more natural transformations that relate the product of any object with a unit on the left and on the right. So left and right unities. And we are requesting this structure to satisfy certain coherent axioms. So one is the pentagon. This is to assure that if you have 4 objects and you multiply them in either way, so and then relate these multiplications by the associators, everything works well. I mean, as it should. And then also similar conditions for the unities. So examples, let me just give you some. I mean, if this is the first time you encounter this, don't be scared, please. I will start with, I mean, this category that I mentioned before, back. So, I mean, this category of finite dimensional vector spaces over K. These also are the objects, the morphisms are linear transformations. Then, I mean, the tensor product is what you expect. I mean, tensor product over your base field. The unit in this case, by the way, I hope you're seeing what I'm writing.
We can, yes.
Yes,
Thanks.
good. Yeah, just checking. The unit is the base field, and associator left and right unities, they are the obvious ones that you may remember from linear algebra 1. So let me just give you a slightly more interesting example. So groups, this case, tensor product, is your direct product of groups. The unit is just the trivial group, alpha, L, and R, also obvious. The obvious ones from, group theory. And well, now that we are talking about representations, well, why not? Something slightly more fancy. So this is the category of representations of G over this base field K. So like this G going to GLP. And I mean, my tensor product of vector spaces, of representations from the Dijkgraaf vector spaces. L given by this, where you take an element in the group and you send it to the tensor product of the image of G under the representation rho V and rho W of G. And what for the unit, well, this is for the tensor product. And for the unit, well, you have G going to GL. Okay, so this is your field without zeros, and then G is sent to identity in K. And that's it. So once you have your monoidal category, I mean, how can you relate this to? You didn't know this is through functors, but then, I mean, we want to actually preserve a certain amount of structure in here. So if you give me 2 monoidal categories, I'm going to define a lax monoidal functor consists, to be a functor between one category and the other, and then a natural transformation that relates the image of, the product of 2 images with the image of a product, of a tensor product of objects in here, and a morphism that relates the unit in the resource category, well, in C, with its image in D. So, I mean, in a way that this is, so, I mean, everything is compatible with the monoidal structure. So if you have a monoidal category on one side, and then you use this natural transformation, you need to check that these natural transformations, they are compatible with the associator, with the unitus, so, and this morphism with the unitus, and everything works well with each other. So this is lax, but if I say oblax, then I kind of reverse the arrows somehow. So an Black's monoidal functor will be again a functor, but then this natural transformation will have like reverse direction. So you take the image of a product and you relate it to the product of images, and you relate F1 with 1. And similarly, I mean, you need to take care that, you know, all the monoidal structure in both sides is compatible. I mean, that once you act with the functor and everything works well. So, but what I mean by a Frobenius monoidal functor that I was mentioning, this is our main tool. This is a lax functor, monoidal functor, and also an oblax monoidal functor that in addition satisfies some certain compatibility conditions between these two maps. So between mu and nu and these two morphisms. So actually, if you are familiar with Frobenius algebras, which I will define in a second, it's actually a very similar condition in graphical language, if you're familiar with that. It looks like this. I mean, it's just a way of relating, making sure, well, it's just some condition relating these morphisms using the associator and so on. I mean, it's a little bit lengthy, so, but if you're curious, we can discuss more about it. So separable, I mean, if you find this adjective in front of your functor, actually what it means is that these two morphisms in here, one is like the inverse of the other. So if you compose, then you get the identity. And so, great. Actually, separable Frobenius monoidal, this is going to be the functors we're going to use. Spoiler, I mean, they're going to be this way, which is why I'm introducing them. So I will give you just an easy example. So forgetful functors, these are like the most classical monoidal functors. So if you have, let's say, vec, and you go to the category of sets, forgetting all the vector spaces structure, then, I mean, that's one case. But since I'm going to go into a little bit of detail later on one case of these functors, I will just postpone a second example to then. So back to categories. I mean, I want to introduce some structure. I'm not going to stay only on monoidal. I want to put like quite a bit in here because we will use it later. So if I have a monoidal category and introduce a number of properties, namely k-linearities, that means, roughly speaking, I'm avoiding some technical details, that the Hom spaces there in my category, they are k-vector spaces. So local finiteness, that means that these vector spaces, I mean, which are the Homs, they're actually finite dimensional. Doesn't matter which two objects you take. I mean, they're always finite dimensional. Also some extra conditions in here. Abelian, that means the 6 co-kernels. We can have short exact sequences in your category. So great. Then if I assume that 1 is a simple object, so I cannot break it into smaller pieces, or equivalently, I can take the endomorphisms of 1. I mean, and this happens to be isomorphic to K, then that's an extra condition. And then rigidity. That means that there exists the notion of a dual. So like for every object, I have another object and morphisms relating with these two satisfying setting compatibilities, which we get one with each other on the left, on the right, and blah, blah, blah. So that means my category is rigid. So if I have all these properties, I will have what is called usually tensor category. Some people just make this to use indistinctively monoidal and tensor, but I prefer to, be clear what I mean. So if I also have finiteness, that means that I have finitely many simple objects up to a certain equivalence relation, and semi-simplicity, which is like having a basis for your category. So like every object in your category can be written down as a direct sum of simple objects in your category. Then if you have these three things, you will have what's called a fusion category. And then if you have a certain notion of a braiding, so if you have two objects, you braid them, never better said, and satisfies some certain non-degeneracy condition, well, long story here, then you will have what it's called a modular tensor category. So some examples, let me give you some examples of these categories. Because I'm just going to be using them. This vector omega that I was mentioning before, let me just be slightly clear and tell that this is the category of finite dimensional G-graded K vector spaces. I mean, G is a finite group, finite way. So, I mean, the symbols, I'm going to denote them by delta G. This means that this is the K in degree G and 0 else. And this omega is actually a 3-cos cycle that actually in place with the structure of the category, because if I take the associator, actually what I get is this cocycle, this 3-cos cycle, times identity in here. So like, I mean, and actually it's a 3-cos cycle, the 3-cos cycle condition is exactly what you get when you compute the pentagon axiom for this one. So once, I mean, this is the first example, let me give you another one, fusion category. So let me take C. I mean, with this case, for example, if suppose you have the previous one. So if you have C fusion, you can define the center of C. So this curly C, sorry, curly Z, G, this is the category. Whose objects they are actually given by pairs. So think of their pairs. So C omega. So the C is an object in my original category, so it could be something in here. And this gamma here, this is a natural isomorphism. So that takes, I mean, for if you have, there's one for each object, and then like, I mean, it relates the product of this object and any other object, and be super, I mean, like in whatever direction you compose them. So and of course, I mean, this pseudo braiding, I mean, this braiding needs to be compatible with the associator, of course. I mean, what we know is that actually the center of each, the center of a category is also fusion. This is a result by Dijkgraaf and sorry. Nishik and Ostrich. Dear God, I hope I wrote it correctly. Although, I mean, let me just mention that, by the way, this is what I want to say. I mean, there's some requirement on the, I will say this, on the base field to be algebraically closed and characteristic 0. So roughly you have now I mean, with these two things, you have an idea of the category of Dijkgraaf-Witten, but I will go into more detail in a second. So let me just give you an example for modular tensor categories. I think you never had enough of this with VOAs, but yeah, it could be, sometimes they are easier. So for the Fibonacci category, that's the easiest I really can think of. So you have just two objects. And the fusion rule, it's something really simple. So you multiply these. Oops. The final, and then this. Oops. But of course, I mean, well, of course, I mean, we call this, I mean, the Fibonacci because the categorical data. So actually, the quantum dimension of this object X depends on the golden ratio. We choose that one. But of course, I mean, given the audience, our favorite ever modular tensor category is the one given by IVOA. So if you have mu to be rational, well, a nice, let's say, rational C2 cofinite. Vertex superior algebra, well, then the category of representations of this guy is a modular. But okay, I mean, I want to focus on the case of set. I mean, on the case of the Dijkgraaf-Witten categories, because actually, I mean, I told you here that they are fusion, but actually one can go a little bit more and see that they're modular. And actually, that was very useful for us. I wrote down here in like step-by-step detail. So, of course, I mean, I have told you how to see this using vec omega and this half rating associated to it, but actually it is super useful to, in our case, it was very useful to observe this category via the structure of the so-called Yetta dreamful modules over a group algebra, and actually twisted, not exactly. I mean twisted because, well, I mean, like the action is kind of tweak with some cohomological data again. So if you never saw a Yetta dreamful module before, I mean, let me just tell you that this is actually a module over the, I mean, well, in our case, a group algebra. It can be generalized to something like all the kinds of algebras. A module over the group algebra. It is also a co-module over again the group algebra, and it satisfies the so-called Yetta dreamful condition. So like there's a certain I mean it looks like this in graphical notation. It's I mean somehow how to explain? I mean, like it's a certain condition related to the action of the group algebra on your objects. And also, I mean, to relate this, it needs to be behave in a certain way related concerning braiding. Well, something is like involved to but it looks so this beautiful. Just keep in mind module, a co-module, some condition in there. That's it. That's everything you need to know. So using this structure, let me just describe it. So if you have G, a finite group, I mean, again, W, an object in here, I mean, in my category, which is G graded, then I can define the action of the group algebra into here as this. And it needs to satisfy the following. So if I have, I act with a first object, so if a first element of my group algebra into the dth component, and then I act again, then I will get a certain function, tau, here, depending on actually these H, this G, and this D. All of these are elements in my group, given this. And in fact, this tau here, it can be related to the 3 cocycle of the category in this way. So it's this product of 3 different things. For the tensor product in my category, so if I have 2 such V and W, so 2 elements like this, I can, the dth component, it will, in my tensor product, will be given by this. And again, the module action, if you act with a certain element of your group algebra into the product of these 2, it will give you some, and again, some cohomological function again, times this, and this is again like some big quotient of 3 cocycles up and down. Hope that's okay with everybody. Are we good? Any questions so far? Are we fine? So like, this is just, I mean, like actually not, like this is a well-known structure. I mean, like twisted rigid Trimford module. The thing is that, I mean, there's always this cocycles appearing up and down, and actually they played quite a nice role afterwards. I mean, just to finish this introduction, I would like to give you 2 more definitions. So one is our main character, which is the definition of an algebra. By the way, I'm assuming here fusion category, but I mean, algebras can be defined like in a much more general setting. So this is just your generalization of algebra, of K algebras, but to the setting, the categorical setting. So triples, A, M, and mu. A is an object, M a multiplication. So I mean, the map relating 2 copies of A to A, and U relating the unit to A, satisfying unitality and associativity. So like the usual in graphical language, associativity and unitality. Well, similarly for the co-algebra. So, but just reverse the arrows again. So like co-multiplication will go this way, co-unit will go this way, co-associativity, co-unitality needs to be satisfied. And again, Frobenius algebras, well, if you have Frobenius algebra in a category, then I mean an object, which is an algebra, a co-algebra, and then multiplication, co-multiplication, unit and co-unit need to be compatible again with each other. This condition I was mentioning before. Sorry, in graphical language. Examples. Well, easiest case I can give you of the category is just a unit. I mean, that's the easiest thing. And I mean, as I was mentioning in the introduction, so vec G, and I'm setting the identity, so the cocycle to be the identity simply, well, the identity, sorry. It should be E1. So an possible algebra in here is just a group algebra. So for L, a subgroup of G. And in fact, G omega, as I was saying before, I have these twisted group algebras. I mean, from this result by Ostrich and Natali. So this psi here is actually a 2 chain. It needs to satisfy a certain condition relating it to the three co-cycle. I'm not going to go into that into detail. Let me just say that one can write this down, this guy's down as this in terms of the symbols and the multiplication. Given by, so if I take, oops, sorry, these two, then I should get this two cochain taking entries with this G and G prime times a simple in the degree given by the product of the other two. So this is what it's called twisted group algebra. I mentioned in the introduction. So these are three like very concrete examples. And easy actually. Why am I introducing these algebra? I mean, like the algebras, and that why I'm in particular I focus on the case of Frobenius monoidal functors is actually because Frobenius monoidal functors transport algebras to algebras. So like if you are, I mean, if you have an algebra in some monoidal category and you apply a monoidal functor to a Frobenius monoidal functor to it, whatever you get, I mean, the image of this algebra is going to be again an image. So it's like, it's good because that tells you, okay, if you're in an easier category, so of saying, and you use a functor to jump to a more complicated one, hey, you got it. Like it's transferred straight away and you already have a straightforward the algebraic structure. So it's like one thing that you can count on. Let me just refresh some adjectives that I use for, that are used for the algebras. In decomposable, if you kind of break it down in smaller pieces, so it's not isomorphic to a direct sum of some non-trivial algebras. Connected is actually the dimension of the Hom space between the algebra, well, the unit of the category and the algebra is just one, it's something very small. Separable, if you have some sort of co-multiplication with satisfying setting conditions. Commutativity, if you have like, so, you multiply two objects and this happens to be the same as if you grade them and multiply them again. So like really changing the position doesn't change anything. If you combine these two, we will call it a tau. If you combine connected, commutative, and a special, which is well, one condition of a Frobenius algebra that, satisfies that you should compose multiplication and co-multiplication. It should give you the unit times some number. Similarly with unit and co-unit. If you combine these three, you get what is called rigid. And just to follow up with the previous example, the twisted group algebras I was mentioning before. In vec G omega, they are actually connected, indecomposable. Indecomposable, so special as well. And separable. And actually, if you remember that I was mentioning these twisted Hecke algebras at the very beginning, they are actually also indecomposable, special, and separable, but not connected. If you're curious, our paper. All right, just very quickly, some structure I would like to mention that was super useful for us in our very lengthy calculations was the notion of module in the categorical sense. We find a right module of a certain algebra in a category as a pair of an object, which is, of an object in my category together with an action satisfying compatibility with multiplication and the unit. So really there's no same notion of a module over a certain algebra, but in the categorical setting, one can the same thing do with left and right and bimodule. And we say a right bimodule is local if actually you twist, so you break, algebra and object, you break again and act, it should give you the same as if you just act, and so nothing really happens. It's kind of transparent. With this, guys, we can construct a category, reblog, which I am mentioning because of the following result that we proved. So if C is a modular tensor category and A is a rigid Frobenius algebra inside my category, then this category in here is also modular. And why this is important? Well, it's because in our case, we applied this to the Dijkgraaf-Witten. We took one particular case of a rigid Frobenius algebra, and we used this category as some sort of intermediate category to make calculations. And that was great. But now let's go into the more, how we did this classification. Now that I have to said all the background I wanted. So to begin with, we constructed a functor in the following way. So we have a G group, we have a certain subgroup, and some 3 cocycle, and I want to go from this category, the center of big H omega, going to the center of big G omega. So like this is the category we want, like the big one, and this one is like a slightly smaller one. And how do we do this? Is by taking one object in here and we map it to the following. We define the image of this functor as the product of the group algebra times V. And it's like, hey, that's something pretty easy. Like you just, take this V, to just multiply with the group algebra to provoke it to be an object inside here. Done. Well, actually, something this simple, it was actually super effective because we prove that actually this is a separable Frobenius-Moreno functor. Not only that can bring you from like this smaller category into the bigger one, but also, gives you something more. In fact, this I defines an equivalence of monoidal categories between this and this category of local modules I was mentioning before, which lives inside the Dijkgraaf-Witten category, where this algebra here needs to be taken as the image of I, the image of the unit under this functor I, which, by the way, happens to be a rigid Frobenius algebra in Dijkgraaf-Witten. And the thing is that using this result, it was like a good way, like a good path to allow a lot of calculations on the Dijkgraaf-Witten categories, because using this, we could jump straight forward to here, and then we could, push forward the classification into here. As for the algebras, I made a first slide, and then I will show you, the gory condition, the tricky conditions appearing here. But for the algebras, please first consider the K-vector space B. So this has elements En. N is a normal subgroup of H, the subgroup. This kappa here, this is just some function for now, going from 2 copies of this normal subgroup into the field without zeros, and epsilon going from this, the subgroup and the normal subgroup of the subgroup into the base field without zeros, and define the multiplication between these basis objects with some function here, some entry in here, and multiplying everything in a very simple way, and this is the unit. Well then, actually this is actually super nice. It's a connected commutative algebra in the Dijkgraaf-Witten category of H. And now let's have a look at what happens in here. Because, these functions, although in the very beginning we were like, oh, okay, some function in here. Well, actually they are related to the 3 cocycle in a very nice way. So like our omega needs to be related to this kappa, because it needs to appear as this product, of 4 different kappas. There is some normalization condition if you happen to have the unit of the subgroup. And this is how you relate tau and gamma. Remember, tau and gamma appear as part of the structure of the Dijkgraaf-Witten modules. And this is how you relate them to epsilon. And here, how you relate gamma with kappa and epsilon, and how you relate kappa with epsilon. And okay, I mean, like, just, you know, it looked like a lot of, like, a really a massive salad of cohomological stuff. But okay, I mean, like, actually, it wasn't too bad. Because the thing is that under some assumption on the order of the normal subgroup, we could prove that actually these algebras here, they are rigid Frobenius algebras. And actually, I mean, one could describe the coalgebra structure in a very nice way. So, like, the co-multiplication could be described in this way, just some product of basis elements with some kappa going on. The co-unit, I mean, it was just a delta, something really easy. So the thing is that probably at this, you may be missing some sort of normalization condition for the epsilon in here. Well, actually, this normalized condition on kappa together with these two conditions in here implies some normalization condition on the epsilon. And as I was saying, I mean, like, at the beginning, it was like, ooh, wow, that's a lot of functions, dear God. I mean, like, this is quite a salad of numbers. God, dear God, what is this? Well, the thing is that this set of conditions that I was describing before, well, that I was censoring before, this and this in here, actually had a meaning, and actually a beautiful meaning. The thing is that this is actually related to, I mean, the cohomology of cross products of groups. And these conditions, they are equivalent to this condition on the total complex that one can define, I mean, using these normal subgroup, the subgroup and the group all together. And it reduces into something really, really synthetic, really nice, really simple. And there was an explanation of why we were seeing all these functions here and there, and behaving in this particular way. So just to finish, all right, well, you know, we have the functor, we have the objects, all right? So, like, and what do you say? Use the functor, I mean, from one side to jump to the other side, and we will still have our algebras. So what do? Let's have a look at the image of these algebras in here under the functor I. Let's call these guys A. And actually, one can describe the structure of these Frobenius algebras. Well, I mean, like, as a Frobenius algebras, this A, this is the quotient K vector space spanned by these guys. I mean, this is a certain relation that these A's need to satisfy, where, again, tau and epsilon, I mean, cohomology, again, playing around, play a role. This is how the multiplication goes between two differing objects. So, like, there's some gammas and some kappas appearing, again, some extra conditions. This is how the unit works. This is how the co-unit works. For multiplication, again, some gamma, some kappa. So, like, it's I mean, like, again, a lot of functions happening going on. But I mean, like, you can describe this structure, I mean, of the algebras very nicely and very concisely. So it's really good. All right, and finally, the big theorem. So under some conditioning here, again, on the order of n and the quotient of G and H, then one can prove that A is actually a rigid Frobenius algebra in the final Dijkgraaf-Witten category. And okay, you have this algebra, but actually we could reduce this more and prove that actually every single rigid Frobenius algebra in the Dijkgraaf-Witten category is actually isomorphic to one of these A's that we have described in a very precise and concise way. of course, I mean, some choice of data, and there's this condition on the order of the subgroups. I mean, just playing around here and there. So we made it. That's it. I mean, like, we found the algebras. We gave them like a precise description. We have the functor, which is incredibly simple, but actually really, really nice. And I mean, when we actually managed to prove that every algebra that we can have in this case is actually of this shape. So, fantastic. So go us. I mean, like, what actually comes next? Well, I mean, actually, this functor that we came up with, I mean, the functor I, it was kind of inspired by a previous functor that we had worked out in this woman in representation theory collaboration with Plavnik, Wilton, and others. The thing is that they are pretty similar. So we took, I mean, this tensoring with the group algebra on one side or on both sides for the case of the phi. They're a very similar strategy. And after conversations with our colleagues, I mean, from in Belgium, in fact, I mean, actually, this functor seems to appear in other very similar contexts. And so it's like, what's going on? Like, why is this always working? When does it fail? And how can we apply to other places, like the study of representations of I mean, something like representation, negative representations of some half algebra, something like more fancy, like, okay, I mean, like, how much can we stretch this? And if it fails, okay, why? So, I mean, again, as I was mentioning, can we use them in representation theory of half algebras for some half algebra with some adjectives, suitable adjectives, and by the way, in some other cases where I mean, not only the representation category, but actually also the center, so like as we did before. But probably, I mean, for the audience in here, I mean, my biggest question will be, as I was bugging Sven the other day by email, what happens to vertex operator algebras? So it's a well-known story. I mean, you can use algebras in these categories to construct another holomorphic VOAs. So, and this is actually the same way that, I mean, how the Monstein VOA was constructed. If you take the Leech lattice VOA, and it's a very, very simple group, which is set 2. So like in this case, what do we have? We have like plenty, like we have every single algebra that you can have. So if we take all these algebras and, I mean, compute like every single possible orbifold VOA that we can, that we can construct, do we get like any exotic, any nice, well, the not so well-known VOAs? There's some work done already in the case of permutation. What's it? Permutation VOAs, worked out by Di Evans. I mean, also here from Cardiff, and Terry Gannon. So like, I mean, but maybe that's something worth, I mean, checking out, because, well, I mean, we have like very concrete descriptions. I mean, so it probably will be interesting to understand from the VOA point of view what's going on with all these cohomological functions. So like, I think there's plenty of things to at least have a look at and probably explore. Yeah, and more things, I mean, like to do. I don't know, I mean, like this, if it's only, I mean, there's plenty of other things I would like to test next. Well, I mean, one is extracting ways for the techniques, the functor, I mean, and probably other cases of all the interesting categories, I mean, with interesting algebras to classify. And of course, there's always this VOA thing that completely steals my heart. But I guess that for today, this is it. So Dijkgraaf-Witten, thank you very much for your attention. And please, if you have any questions, go ahead. And if you prefer to do it later, just send me an email. I will be very happy to reply.
Thank you so much, Anna. Thank you. Let me
Thank
stop the
you.
recording so that we can ask more freely. Thank you very much.